Welcome to Nano Matters, the podcast that explores examples of nanotechnology. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today, it's my pleasure to welcome Vinayak Dravid, the Abraham Harris Professor of Materials Science and Engineering at Northwestern University. Vinayak, thank you so much for joining us today. Can you tell us a little bit about the research that you're doing at Northwestern?
Yes, in one area of our research, we're working on how to use nanotechnology for environmental remediation. And this idea comes from the fact that for the last 2.5 centuries of industrialization of Western society particularly, but also now throughout the world, there's a legacy of pollution that has accumulated, ranging from oil pollution, because that has been the primary source for energy and materials in our world for the last couple of hundred years, to nutrients and fertilizers which run off from agriculture and contribute to contamination in waterways. These are all gigaton problems, right? There's a massive problem, whether it's water pollution, microplastics. So the solutions have to be proportional, correct? You need to have solutions that are compatible with the scale of the problem. And that is often a challenge for academic or scientists because we typically start with laboratory scale research. And to go from lab level to commercial is a massive challenge. And it's almost the chasm that we call it valley of death, right? And so we wanted to start with the capabilities of platform technology, which has the potential to address this gigaton problem. That's where we came up with this concept of sponges or membranes, because normally these are often discarded. They become actually landfill. So instead, if we can use a very thin coating of affinity for pollutant as a coating on these sponges, then you get the best of both the worlds. One is, instead of disposing and creating a landfill mess, we take that sponge, add a very thin coating of affinity for that particular pollutant. So sponge is now our platform. It's like a Swiss Army knife. So one aspect of the Swiss Army is like a knife. You can cut fruits. Maybe another, you can remove the cork from the wine bottle, or you can get the idea. But here what we are using is sponge as a platform for a specific affinity for pollutants. So our major first discovery was OHM sponge. And it stands for, O stands for oleophilic. It attracts oil. H stands for hydrophobic. It repels water. So when you have oil and water mixture, you want it to be separated. And that's a very challenging problem. And M stands for multifunctional. In addition to removing oil and water, what other functionality? And M in some cases stands for magnetic, because especially if you want to use robotics and other ways to have little human intervention, having a magnetic way of manipulating structures makes sense. So last year we had this breakthrough where we showed that very tiny amount of carbon and iron-based slurry can be dip coated with the sponge, and then you have a very thin coating of this affinity, and that has affinity for oil. So in a mixture of oil and water, it absorbs only oil and leaves behind water. And then you squeeze the oil, and then you recover it, and then you can reuse it. So we call it the story of R. You reduce the material that you use, which is a thin coating. We reuse the material because you have the ability to recover. And that's where you recover oil, you recover and reuse it. And then in the process, you're restoring the environment. So that concept of R is something we're very excited because it has the potential to scale, be cost effective, and can be deployable. And a lot of environmental technology, the challenge is there is a process in play for many, many centuries, a couple of centuries already. So you don't want to do something that's going to disrupt. So you want a so-called drop-in technology. You don't want to do anything very dramatic. So dip coating is a very simple process that's been going on. People have been dyeing saris and other clothing for centuries. Same concept. You take sponge, dip coat it, squeeze it, and it's ready to use. And it has affinity only for oil and not for water. So it keeps on sucking up oil, you recover it, and that makes it environmentally very friendly technology.
So that's a really exciting technology to be able to separate oil from water, which is a real challenging problem, as you mentioned. I understand you're also working in agricultural settings and looking at phosphates. Can you describe what phosphates are used for and how you're addressing those materials?
Oil is one example where you can see the industrialization led to the legacy issues of pollution. Another legacy issue, particularly last century, I often ask in my freshman course, that is, what is one technology in 20th century which made the most impact, positive or negative or otherwise? And people talk about cars, information technology, but perhaps the most intriguing answer is fertilizer, because you could make food out of it, and fertilizer can make bombs. And unfortunately, that is the legacy of 20th century. Also, the two world wars we fought, and so that gave you a sense that this is a technology which can do both kill people but also nourish people. And over the last couple of 100 years, this fertilizer has become a real challenge because phosphate, particularly, is required for health of plants and humans as well, because the backbone DNA is made of phosphate. Energy that we make in every cell is a phosphate. So as a result, phosphate are very important, but it's a non-renewable resource. It actually comes from the rock, phosphate rock. And unlike nitrogen, which has a gas, so there's the ability to fix nitrogen through a gas phase. Phosphate does not have a gas phase. So once you derive phosphate from the rock, unless you recover it properly, manage it properly, it becomes basically diluted and become waste. And we have limited supply of phosphate, and that's a real challenge. So you have both. There's a limited supply. And secondly, the excess phosphate that goes into waterways creates this terrible problem of algae bloom. If you see in Lake Erie, Gulf of Mexico, many Great Lakes, especially during summer, when excess phosphorus is released, that provides the food for algae. It might be great for algae, but it creates this blanket of green goo, and that reduces oxygen intake. So flora, fauna below are compromised. It's called eutrophication, so the loss of oxygen. And that's a massive problem, both ecologically, but of course, environmentally. And so if we can recover the phosphate and reuse it, then you solve both the problem. One is the supply side, but also on the demand side. And so we found out that our sponge technology, all we need to do is change the coating a little bit in order to have affinity for phosphorus. And that was a Proceedings for National Academy of Science paper that came out just a few weeks ago, where one of my students showed that using magnetic nanoparticles of iron oxide, which are truly nanotechnology product because they are so-called super paramagnetic, they have extremely high affinity only for phosphate. So when we use actual water sample from Chicago Reclamation, where they use phosphate removal as a part of it's the world's largest cleanup facility for water. And that sample we use to show that all the other ions are left alone. Only the phosphate gets sequestered. And that is exciting. And the only parameter you need to change is pH. It's very simple. So again, it's the same concept, drop-in technology that does not change the process flow. Just one pH where you sequester phosphate. At a slightly different pH, you release it and come back. So this ability to reuse, recover is now again applied to phosphate. And that's also exciting.
So you're able to remove the phosphate from the water, and it's considered a pollutant there. Are you able to collect enough that you can actually capture that and reuse it in agricultural settings, for instance?
Absolutely. And so you can imagine that nanoparticles by themselves can also sequester, but then to manage, deploy is a very challenging problem. So all we are doing is we are taking the nano, anchoring it on the sponge so that it doesn't release and it absorbs. And it turns out that the ability of this nanostructure to absorb phosphate is 99%. So you can imagine almost all of it can be captured. And then we go to a different tank, change the pH, release it, and it creates eventually what is called as phosphate brine, which is a precursor fertilizer production. So you can see the pure circular economy in play here. So we have a sponge, we can sequester phosphate, recover it, can be reuse it many, many times. So in fact, some of our calculations show that it's 1,000 times less waste than any conventional approach that you use. Currently, they use alum, which creates this massive toxic sludge, which becomes a landfill problem. And then when it rains, that sludge phosphorus goes back into the lake. So there are thousands of such so-called phosphate ponds throughout the world, throughout the country, and particularly in South Florida, it's a huge problem because we have this massive phosphorus-laden holding ponds. There's a risk of release, and then when it releases, it creates algae bloom and all the problems that you see. So we're very excited. The same technology that removes oil with slight modification, has the ability to sequester phosphate with such a high value. We are very excited.
So you've talked about how this technology can be used for phosphate or can be used for oil. Can you describe a little bit more how you go about coating the sponges, and with respect to scaling up, are they synthetic sponges primarily? And how would you go about doing that?
Great question. Again, there are two types of sponges, correct? So in one case, we want a lot of water, aqueous flow to occur. In a case, for example, in a situation where there's a majority water and a minority oil or a minority pollutant, right? So there you want all the water to flow. So there we use cellulose-based sponge. So cellulose is like our household sponge, as you know. We put some soap on it, we wash dishes. In fact, ever since this technology happened, I volunteered to work in the kitchen so that I could understand the process of sponges and membrane. So on one hand, you have cellulose-based sponge that has ability to flow water, and the nanotechnology slurry gives us the small, thin coating that adheres extremely well in the cellulose. In the other end of the spectrum, we use polyurethane or polypropylene, which are hydrophobic sponges. And those are the ones which are typically used for oil spill remediation. So there you prefer not to have water. So as a result, you want the intrinsic substrate to be water phobic, and that's hydrophobic, and that is polyurethane, polypropylene type sponges. But again, the active part is still the thin coating that applies on the surfaces of the sponges. So you have one hand cellulose, the other hand polyurethane, cellulose based for very large water flow, like in phosphates, for example, or minority oil, fracking water, because if you use tar sand where you have a lot of water and very little oil. And in the case of oil spill, it's this polyurethane or polypropylene-based sponges, which have the affinity for oil, but they reject water. So that gives us the two scalable solutions for remediation.
Well, I think that you've already identified, I think, what you called gigaton problems. These are huge problems. But do you have other target pollutants that you're exploring for this technology in the future?
Excellent question, too, because you can see that oil is something we demonstrated, phosphate just recently. So in this spirit of Swiss Army knife concept, you can imagine the substrate is still the same. And if we change the coating, we can tailor it to, for example, heavy metal. So in different parts of the world, including in US, as you know, with this terrible situation with flint, lead contamination, or the parts of eastern India and Bangladesh, where arsenic is a problem. There are different parts of Africa where cadmium and other metals are a problem. So we found out that our coating has the ability to sequester heavy metal, and then we derive that affinity through innovation in our nanostructure synthesis. So we have developed a flow reactor that gives a tremendous synthetic capability using aqueous system. So even synthesis, we want to make sure we stay away from organics and other toxin substrate. So using water-based precursors, you improve it's a green chemistry, and it has the ability to sequester heavy metal. So you can imagine going from oil to phosphate to heavy metal. And one last thing I'll leave it as an intrigue for you is radioactive nuclei. So one of the beautiful advantages of OHM sponge is magnetic, so it's compatible with robotics. And so as a result, if you have contaminated radioactive nuclei, such as cesium 134, 137, our structures have affinity for it, and then you can use a magnet to remove it, so you don't have human intervention. So that's in the future. And so for now, oil, phosphate, and heavy metal are our immediate targets.
Well, thank you so much for describing your work in environmental remediation to us today. Do you have any closing thoughts that you'd like to share with our listeners?
Absolutely. I think one thing we often talk about when it comes to environmental remediation is the right thing to do. And nobody questions that. So it's not just about doing the right thing, but it can be a business. It can be value. So now more people and more design criteria now include the burial aspect of a technology from start to finish. In the past, it was all about cost of purchase. What nanotechnology showed is the cost of ownership. It's not just that you buy for a certain price, but how do you sustain that? So if you use a nano-enabled product, you may use less energy, less water, less maintenance, and that adds value. So even if initially it might be slightly expensive, during the duration of the ownership, it can be considerably profitable or at least economically feasible. So I think the main message is that environment can be a business and it can be a viable business. So you can do both good and do well.